All right, trying another video solution here. This is the ideal gas law. Looks like we can write it as PV equals to capital N Boltzmann's constant times temperature. That's one option. And another option is PV equals to nRT. So really the difference here is in the constant and then how we label how many atoms do we have, because this is how many moles, and so this is like grouping them together. This is literally, just how many are there. And if you read this question, it says an expensive vacuum system can achieve a pressure as low as 1 times 10 to the minus 7 pascals at 20 degrees Celsius. How many atoms are there in 1 cubic centimeter at this pressure and temperature? So since the question asks for how many atoms, maybe I'll do this one. Although I must admit, it's the same as this one, except here I would solve for the number of moles, and then I would have to use Avogadro's number to convert it. And of course, that's the difference between Boltzmann's constant and the ideal gas constant is Avogadro's number. So, as I was trying to explain in the video lecture, these are really the equivalent. And I'm going to go ahead and go this way. Being the physical scientist that I am, I really like this one because it goes directly to how many atoms there are instead of how many groupings of atoms, how many moles. But when you're in the lab working, and those of you coming from chemistry, you're working along, you tend to group them in moles. And so you might feel more comfortable with this one. But let me go with this one. And so let me solve this for N, because that would be a PV and then Boltzmann's constant times the temperature. Now, of course, the other thing I want to add to this is make sure, as we talked about, that our pressure is in absolute and our temperature is absolute. In other words, on the Kelvin scale. Volumes are always absolute. But all of these have to be absolute. They have to be, not relative to some other thing. They're from, nothingness. And so nothingness means zero pressure. And then, of course, zero motion goes with 0 Kelvin. Okay, so coming back over here, they give us the pressure. The pressure is really low. And that's what they say here. This is a good quality vacuum system. This is not your common household vacuum that you use to pick up dirt. This is a high research facility where you're getting rid of all the atoms, and so maybe you're making semiconductors and you want to get them pure. You don't want to get any dust or molecules in there. So you've got that low pressure. Now they say the volume is 1 cubic centimeter, so maybe I'll write that as 1 centimeter cubed. But as you've seen me do before, centa means 100th, and we can quickly just replace that with its number in cubic to get how many cubic meters. So I eventually want that to be cubic meters. Boltzmann's constant is that 1.38 times 10 to the negative 23, and the units would be a joule over a Kelvin. And now maybe an easy thing to overlook is to remember that the temperature needs to be on the Kelvin scale, and they say 20 degrees Celsius. So I need to add 273 to the 20. So 273 plus a 20 makes 293 Kelvin. So if I put the numbers together, so I'll go 1 times 10 to the minus 7 for the first number. And this number, as I said, if you'll let me put the cube on the centa and the cube on the meter, this is actually then 1 times 10 to the minus 6. Because a centa is 10 to the minus 2. When you cube it, you just multiply exponents. And so that's 10 to the minus 6. And then down here is the 1.38 times 10 to the minus 23rd, and the temperature is 293. Now, also working over here with my units, I would take Kelvin and cross those out. I would notice here that the meter is cubed once I distributed the exponent. And then meters squared would cancel with 2 of them, leaving me with a Newton times a meter, which is a joule, which would cancel that. So those all cancel beautifully, and maybe I should just put nothing or nada here, right? There is no units left over, and that's actually perfect. That fits my unit analysis, because my unit analysis is asking for a number. There are no units. You know, how many students? 12. How many cookies? 3. How many gallons of gasoline? 13. You know, it's just a number. Sometimes we'll clarify it by saying, oh, that's 13 gallons of gasoline, but that's not a real unit, because you asked how many gallons of gasoline. Anyways, so numbers are just that. They're numbers. There's no units with it. So I'm glad that comes out to be nothing, and so now I can take my calculator and go 1 times 10 to the negative 7, and 1 times 10 to the negative 6. Divide it by 1.38 times 10 to the negative 23. And divide that by 293. All right. And despite it being an extremely good vacuum, still quite a few molecules. 1, 2, 3, 4, 5, 6, 7. So this is 2.47 times 10, and I said 7, right? 1, 2, 3, 4, 5, 6, 7 times 10 to the 7 atoms. So we're still looking at, like, you know, close to 25 million atoms in 1 cubic centimeter. And so you're kind of feeling like you got a really good low pressure and there's like nothing there, but there's actually quite a few there, but way, way, way less. In fact, at room temperature, well, this is about room temperature, so room pressure. So at room temperature and room pressure, we would have to increase this to 1 atmosphere, which, remember, is about a 1 times 10 to the 5. So we'd have to go up 7 and then 5 more, which is 12. That's a trillion times more. So, again, sounds like a lot, 25 million, but that's only 1/1 trillionth of the amount that would have been there at room temperature. So the number of atoms is amazing. I think I told you guys, it's easy to forget how many there really are. I held up that little metal bar of copper, which was probably about this big. And that had 6.02 times 10 to the 23rd atoms. And that's more atoms than there are stars in the known universe. It's also more than all the grains of sand. If you added up all the beaches and all the deserts in the world, you wouldn't even get this many grains of sand. In fact, if you added up all the grains of sand on Earth and all the stars in the known universe, you still would be under this number. And this is just a small copper bar. So you just got to be amazed at how big these numbers are when you kind of step back and think about them. It's easy just to kind of thoughtlessly write 10 to the 23rd, but it's an enormous, enormous number. Anyways, I think that's it to the problem. So, all right. Hopefully that helped. Bye.